Right, pressure, volume, fixed temperature. If we do a graph of pressure against volume, like we did with the experiment there, pressure against volume, then we get a graph which looks like this. Okay, it might look slightly different than that on your graph, but that's the way it looks. Now we can't get a relationship out of a curve. If we want a nice proportional relationship, we need to get a straight line in order to do that. So to get that straight line we're looking for, we draw another graph. So if we take all our volume readings, instead of making it V, we do 1 over that number. So if the number was 2, it becomes a half. If the number was 4, it becomes a quarter. So that then goes to 1 over V underneath, and that goes to P on the side. And what we end up with is a straight line relationship. So it should look like that. If we correct for atmospheric pressure as well, we should have a line that goes straight through the origin. Now what that means is, from that graph, is that P is directly proportional to 1 over V. P is directly proportional to 1 over V. And we also wrote that as P equals a constant over V. So that means that PV equals a constant. PV equals a constant. Now I want to leave it there. PV equals a constant. That's for constant temperature, PV equals a constant. So copy that down. That's your new and improved. Dead easy. So the whole point of changing it to 1 over V is that we cannot get a nice relationship from this. So we can't get a linear relationship from this graph. Because this graph will give us a nice direct relationship, which is P is proportional to 1 over V. Right, so next one we had was pressure, temperature, fixed volume. Fixed volume. Now, a graph for that one looked like this. P, T, oh no, all T. Okay, stop talking please. And then your graph look like this on the top. You've already got this, should have this from last day. What we're interested in is figuring out where that line goes to. Temperature, pressure. This line was up here somewhere, and we can expand it all the way back to a point way back here somewhere. Now that point way back there happens to be minus 273 degrees Celsius. Now what we're interested in is finding a relationship here. We want to find a relationship. Now we don't have a relationship from this, it's not directly proportional. We do have a relationship for this. So what we have is a new temperature scale. We say that minus 273 degrees Celsius equals 0 Kelvin. If I also draw a graph of Kelvin, temperature and pressure, it would be a straight line linear relationship. So what we had last day was at 0 degrees the particles will still have energy. Okay, at 0 degrees Celsius, particles will still have energy. We must go right back to minus 273 degrees Celsius before the pressure is 0 pascals. At minus 273 degrees Celsius, the particles have no EK, no velocity to hit the container, no overall force, so no overall pressure. Right. The graph that we had that was a direct relationship was a pressure-temperature graph. Pressure and temperature, however, that's got to be in Kelvin. That's in pascals. Now this will be a direct relationship through 0. That bit there. So there's the direct relationship we're interested in. You don't have space for this graph because you missed it out, don't worry. As long as you get the next bit. But if you have space to put this graph in, put the graph in. The Kelvin scale, pascals. Now what we can get from this graph is that pressure is directly proportional to temperature. Pressure equals temperature multiplied by a constant. pressure over temperature equals a constant. Relationship, which is volume temperature for a fixed pressure. Now this was a difficult one to do because it's really difficult to keep that pressure constant. It's all about trying to change the temperature, change the volume, what happens to them. Now, it's not difficult to understand. Think about it. If you heat up a gas, it expands. If it expands, then it's taking up more volume. So, as volume goes up, as the temperature goes up, the volume must go up. So it must be a direct relationship. Yes. Hang on, let me pause this and let me think about that before I do it wrong again. Now, as I was saying, definitely right, never taking myself for 1 minute. If you increase the temperature, you're increasing the volume. So as something gets warm, as any solid, liquid or gas gets warm, it expands and wants to take up more space. So if we want to look at, as the temperature increases, what happens to the volume? So the temperature increases. Now this doesn't matter if it's a Kelvin scale, a Celsius scale, whatever. 1 unit in Kelvin is the same as 1 unit in Celsius. So it doesn't matter about the scale. What does matter is that if we increase the temperature, we must be increasing the volume. So it must be a direct relationship. That means that V is directly proportional to T. V equals T times a constant. And that means that V over T equals a constant. Right, next thing we need to do is take these 3 formulas we have and put them all together. Taking these 3 formulas, we have our pressure volume, which end up being PV equals a constant. We have our pressure temperature, which was P over T equals a constant. And we have V over T equals a constant. So we take all these 3 together and you get PV over T equals a constant. In other words, P1 V1 over T1 equals P2 V2 over T2. The most important thing about this general gas equation is that whatever one you're keeping constant, you can take out of the equation. So if we take this last formula here, we can now say P1 V1 equals P2 V2 for constant temperature, constant T. We can say any one of the other combinations. We could say P1 over T1 equals P2 over T2, and also V1 over T1 equals V2 over T2. And this one's assuming constant volume, and this one's constant pressure. Kids.